Chanel, go ahead. Sure. So again, we're just going to take some questions from the homeworks. Happy to talk about kind of whatever. Go ahead, Chanel.
Number 6 for L.
Okay. Audrey, you're second up. I saw your hand too. Okay.
Yeah. I was like, what's going on? Okay. Yeah, K was a little Can you do K and L?
Sure.
Yeah.
Okay. All right. So K and L, so 5 is like right there, correct? So K, we're coming from this way. Let's pick a different color, Kulik. Right? So we're coming from the right. So that looks like it's heading towards 1, 2, 3. For L, we're coming from the left. So you're in this zigzaggy mess. That looks like does not exist. And my explanation there would be like, it's that oscillating thing like we saw with sine of like 1 over x, right?
So if it's is it like technically does not exist?
Okay.
Is it because it's at like 2 different values? Like
It doesn't settle to one single value,
Okay.
right? Like it's bouncing back and forth between whatever it looks like 2 and 4, and it never is settling down towards something steadily.
Okay, got it. Thank you. Yeah.
Oh, sure. Audrey, is that
No, I had another one.
okay? But we did okay with K and L, right?
Yeah.
Between you guys both asked for something on there. We're okay with that.
Yeah.
Okay. And the justification's okay.
Yeah.
Okay. What's up next, Odds?
37.
37. No problem. So here it says determine the infinite limit. So I would probably start by just looking at the graph, right? Because we really have only 2 ways to do this, either graph or table. So I'm going to start with the graph because, well, I don't know. It just feels like the easier place to start. And then I'm just going to zoom standard this for now. So we're looking at what's happening at 2. And we're looking at from the right, so it's like this section, right? We're following this down.
Yeah.
Looks like it's heading to negative infinity from the picture. Oops, oh my goodness. If I wanted to kind of confirm that,
Yeah, but I checked my answers with like the back of the book
Mhm.
after I did it, and it said the answer was positive infinity. So I was so confused. It said positive. Yeah, how yes.
it might be a typo in the back of the book.
Okay.
I don't know. Did I copy something in wrong?
I got the same answer. Yeah.
Okay.
So,
Yeah, it could just be a typo on their part.
okay. I like factored it out. Does that make it?
Probably not. You could, and in another section, you're going to see that that's an effective tool for something like this, where you're getting, if depending on the tools we develop in next section, we're going to find ways to do this algebraically, so we don't have to rely on like a picture or a table. Because if we ask you to do this kind of a problem without a calculator, which is a reasonable expectation, you're in a lot of trouble. So that's something that's coming. Odds, you okay? We've decided, I've decided that just has to be a typo. I don't think that could possibly be right. It has to be negative infinity. Chanel.
Number 35.
35. Okay. So again, same directions. So I'm just going to graph this. Notice that I don't have a cosecant button on my calculator.
Yeah, I did know.
But what is cosecant?
1 over sine.
1 over sine. So that's what I'm going to type it in as. So 1 over sine x. And then I'm going to zoom trig this so that I have a scale with pi. Actually, I'm not because it's 2 pi. I'm going to set my own window. I'm going to go from like 0 to 4 pi. And let's go by pi's as my tickies. Oops. And then we'll probably go -4 to 4 or something. It's probably good.
Wait, so what does SCL stand for? I'm sorry.
That's the scale. That's how far the tick marks are apart on your axis.
Oh, got
So
it.
the x-axis, I'm choosing the tick marks to be pi so I can tell where 2 pi is really easily. So like this is 1 pi, 2 pi, 3 pi, 4 pi. Okay, well I only see one part of it. So I'm gonna go ahead and make this a little, expand my up and down because it doesn't seem like I'm seeing what I need to see. There we go. So this is 2 pi right here. So this is 2 pi from the left. Looks like we're heading down to negative infinity.
Okay.
Yep, and that's good enough. You could check it with a table if you wanted to, but I think that the picture's probably sufficient, right?
Okay.
But that's it. No problem. Now the problem would be when we ask you to do this without a calculator,
Oh,
right? But we're not there yet. We don't have any of the tools to do that yet.
okay.
Giselle. Sure. But you have to keep in mind, like, always that any of these problems we're looking at, is this something that realistically can be done without a calculator, and how would we do that? Oftentimes the answer is yes, and it's coming. But you have to remember there are 2 sections of the AP exam that are no calculator. So like all of these questions that we're dealing with, like do they have a no calculator counterpart when we're doing something purely numerically, like we have been. You said which one, 11? I don't know why I grabbed 12 also then. Okay, so we want to start by sketching the piecewise function. To graph a piecewise function, we're just going to graph each piece all on the same axis, and that makes up our graph. So if I look at the first piece here, y equals 1 plus x is a linear function. So to graph that, I just need 2 points to make a line. One part of my line has to be the boundary value. Now I'm going to put a little like star next to that to remind myself that that should be an open circle when I plot that point, because it's a strict less than inequality. When I plug -1 in for x, I get 0. And then I need to pick another x that's less than -1. Maybe I'll pick -2. I get -1 there. So far, so good, Giselle? So if I plot that part, I have -1, 0, and then -2, -1. So there's that piece of my graph. I'm then going to move on to my next piece, y equals x squared, which is what kind of function? Quadratic, yeah. To graph a quadratic, how many points do I need? At least 3, one of which must be the vertex. So for y equals x squared, the vertex is origin 0, 0, right? And then my other 2 x's I'm going to choose are the boundary values for my domain, because I need those anyways. So -1, 0, 1. -1 squared is 1, 0, 0, and then 1 squared is 1. And again, I'm going to put a little star here because when I looked at the boundary value, I had a strict less than at 1. So far, so good, Giselle? Okay. So let's plot those. So I have -1, 1, 0, 0, and then +1, 1. And notice that one I'm putting as an open circle. And I'll make that little part of my graph. And then my last piece there is, again, linear, so 2 points will do. You can always make more, but I don't want to because I'm lazy. I definitely need the boundary value of 1. And when I plug that in, I get 1. And then I need another value that's greater than 1, so maybe I'll pick 2. That gives me 0. So when I plot 1, 1, that fills in the open circle. And then I have 2, 0. So there's my graph. Now the problem asks, determine the values of a for which the limit as x approaches a if f of x exists. So the limit's going to exist for all a except for the place where we have that jumped discontinuity, because we know that the left end limit and the right end limit are going to different values. So we'd say everything for except, or every a except for -1. Does that feel good?
Yeah.
And it's one of these that's like, oh, when you show me how to do this, it's like, that's not, but it's like, what was I supposed to do with that? Right, yeah. And we'll do more with piecewise functions in another couple of chapters, or sections, I should say. If you're not feeling good about them now, we need to get feeling better about them because we see them a fair bit here, especially early on. The AP people love the piecewise functions. So, Chanel.
Number 46.
Sure. Oh yeah, the physics. For 46, how many of us have taken physics?
I did.
You
I
did?
didn't understand.
Who knew the answer to this without even doing any calculus? Does anybody remember from physics what happens to your mass as you approach the speed of light? It's not 0. Oh, it's infinite. It goes to positive infinity. You become infinitely heavy the closer you get to the speed of light. So you might have remembered that if you had a physics class before and talked about, like relativity at any point. That's not an uncommon thing to have talked about, but like for our purposes, I haven't done that. It's not an expectation that you have. What would I do with this? What we're basically asking for is I'm looking at m for the limit as v approaches c of this thing. Right? So, again, we have two methods, graphing and tabular. The problem is that the letters in here are constants, right?
Yeah.
So the v is what our variable would be, right? Because we're worried about v approaching c. Okay? So what I'm going to do is I'm just going to set some values. I don't know. Just do that. Okay? So I'm just going to set the initial mass to be 1 and c to be 2. Anybody remember what c actually is? C is a constant, right? The speed of light. Isn't it 3.0 times 10 to the 8th meters per second or something? Physics people, does that sound about right?
We didn't really talk. I think it's general physics.
Yeah, you might have, you might not have. It's either way, like it's not, it's not that big of a deal. Anyway, so I type this in, right? There's that. And let's just go, that's all goofed up. Let's just do zoom standard. So it looks like this is what's happening here as we're approaching 2. It's heading up. I can't tell, does this keep going up because it's getting super duper steep? or is it actually just stopping? So maybe let's look at a table of values. So I'm just going to pick some values as t is getting close to 2 from below. So do that real quick. So I'll do like 1.99 and 1.99 and 1.999 and see if this is settling down to anything. So that's a rather large jump. That's already past whatever I would have seen on my graph, which makes me think this is just bombing on off to infinity, which is at this point looking likely what's happening, considering it just keeps growing bigger and bigger and bigger every time I add a 9 on there.
Okay.
As we're getting closer and closer to 2, that y keeps getting bigger and bigger and bigger. This looks like it's heading to infinity.
I think I graphed it wrong. I think
Yeah, I mean, it would be easy to do with all the levels in this, you know, and the radical and like everything in the right spot, making sure you're calling the right things constants or whatever.
Okay.
You know, that happens. But that's the idea, which is weird to think, right? Like your volume is staying the same, but you're becoming like infinitely heavy. Essentially, you're turning into like a singularity, like you're turning into a black hole. Weird. Anyways, that's enough relativity for today, I think, right? Last call on questions from the homeworks. Great. So today we're going to pick up with kind of what I had hinted at, where we had talked about, like, eventually some of these limits are going to be things we're going to expect you to be able to do without a calculator. So that's kind of what we start in on today is, what tools do I have in order to start evaluating these limits if I didn't have access to a calculator? If I couldn't just graph this or look at a table, what else could I do, right? So today we're going to build out some algebraic properties that we can use to start evaluating these limits. So these first 5 are just our basic limit laws. So it says for any limits, the limit as x approaches a of f of x, and the limit of x as x approaches a of g of x. If I have the limit of a sum of 2 functions, I can calculate that by taking the limit of each individual function and then adding them together. So I can take a complicated function that is like the sum of 2 things and just look at each of the limits separately. So I can break up some complicated function into 2 simpler functions and take the limit of those simpler things. What does it kind of look like here? Just kind of looks like we're distributing the limit symbol, right? Is that kind of, yeah, number 1. Yeah, right? That's all we're basically saying. If it works for addition, stands to reason it should work for subtraction. It does. So again, you can kind of distribute that limit across the subtraction. If you have the difference of 2 functions, you can break them up into, you know, you want to do the limit of a difference, you can just look at the limit of the first thing minus the limit of the second thing. No?
That's approaching a problem.
Yes. Yeah. If we look at number 3, if we have a constant times a function and we want to take the limit of that, well, we can just pull the constant out front and just have the constant times the limit of the function. Which again looks like, okay, this kind of resembles things I've done. I just factor out a constant. That feels like, okay, that looks, it's how I would hope things would work. Number 4, so if I have the product of 2 functions and I want to take the limit of that product, I can just take the limit of each factor, right? I can take the limit of f of x and the limit of g of x and just multiply those 2 together, which again is taking something complicated and breaking it into simpler pieces that maybe the limit will be easier for. And then the last one, if it works for multiplication, it should work for division as well, provided that the function in the denominator, that its limit is non-zero, right? If its limit is 0, then back to the drawing board, we have something else to do. Maybe not in this chapter, we'll figure out what to do with that, but eventually.
Is it because it's like you can't divide by 0?
Exactly, yeah,
Okay.
right. That's exactly the idea, yeah. Dividing by 0 is undefined. We know that limits don't equal undefined. They either exist or they don't exist, but they aren't ever undefined. And not existing is different than being undefined, right? Everybody okay so far? All right. So let's look at an example here. So here we have two functions that I've defined graphically. The pink one is f of x and the blue one is g of x. And we're going to use this graph to evaluate each of these limits down here. So if I look at example A, a little bit more space there. I'm going to start by applying the product property. I'm sorry, the addition property. To do that, that's property or limit law number 1. Everybody's okay there? Okay. And then I'm going to use limit law 3 on that piece and pull that constant out front. Yeah, look at property 3. Right, I had a constant, and it allows me to pull the constant out in front of the limit. And now I can evaluate the limit as x approaches -2 of f of x just by looking at the chart, or my graph, right? So let's see. -2 is right here. So f of x is equal to 1. Oops, I should say -2. That's the x-axis right there. And g of x is 0. Everybody's okay with that? Just reading it, or I'm sorry, is -1, not 0. So I have 1 plus 5 times -1. That look okay? And we're done. Let's try the next one. So I'm going to start by using property 4 to break that product up. So if I go to my graph, 1 is right here. So f is 2, but what is g? When the limit as x approaches 1 of g, the left hand and right hand limit disagree. So it does not exist. 2 times does not exist means does not exist, right? I'm done. Okay, great. So far, so good. Chanel?
Sorry, so for part A, where did you get the -1 from for the 5 limit x approaches -2?
Well, this is like, that's the origin right there. So this is like -2, -1.
I'm thinking that line.
Yeah. Yeah, so, it just, this is the X and that's the Y. Then it's clear, right?
Yeah.
It's, I read it wrong like half the time also. The grid on there, while helpful,
Yeah.
they needed like a thicker line for the axes
I
or
know,
something.
'cause it won't fit.
So for C, what do we want to do here?
Separate it, use the fifth rule.
Okay.
Well, should we check if len g of x is 0?
Yeah, maybe we should do that. So let's check.
Oh no.
So let's see. 2 is right here. It is 0. It's not undefined. We don't know. All we know is that we can't do this problem yet. The rules that we have aren't going to allow us to do this kind of a problem yet. Because the property 5 does not apply if the denominator's limit is 0, which is what is going on here. So all the tools that we have aren't going to help us do this problem. So for now, it's just something we can't do. We don't know that the limit doesn't exist. We don't know that it's if it's undefined. All we know is we don't have the tools to do this. That's all.
What are we learning about
When?
what? Yeah.
Oh, I'm not positive. Not today. And to be honest with you, it might not even, I'm trying to think of what you would use to do this. I don't know that it's within the scope of this course, to be honest with you. All right. So we're going to continue on. We're going to look at some other properties of limits that we can use. So we're just going to continue on, add in some more properties of limits, and then do some more examples after we burn through a couple more properties. So the next property says, if I have a function raised to some power and I want to take the limit of that, I can just take the limit of the function and then raise that answer to the power. So I can do the limit before the exponent, which is nice, right? Because putting something to a power really makes a lot more complicated of a function. You know, if I want to do the limit as x approaches 1 of x plus 1 to the 54th, you know, like if I can just do x approaches 1, or the limit is of x plus 1, get that answer, and then raise it to the 54th, that sounds like a much better deal. You know what I'm saying? All right. 7 says the limit as x approaches a of c should just be c, where c is a constant. Does that make sense? What's the graph of a constant look like? Horizontal line, right? If you look at any point on there, the limit is just going to be the value of that horizontal line, right? Okay, sure. That absolutely makes sense. Number 8 says the limit as x approaches a of x should equal a. Remember, what does the graph of y equals x look like? Yeah, it's the diagonal line. And what are the points on that line? 1, 1, 2, 2, 3, 3, 4, 4. That the y value should be the same as the x value, right? So if you're approaching the x value of a, you should also be approaching the y value of a, because we know this thing is continuous all the way through. It's connected all the way through. There can't be a jump discontinuity or anything weird happening. Everybody happy there? Okay. If I use those previous the previous 3 properties, we can discern number 9, or we can prove this, actually. So if I use property number 6, that's supposed to be a number sign. That was terrible looking. Allows me to do that. And then property number 8 allows me to say that, which just turns into a to the n. That's just me proving that previous theorem. Yeah.
Wait, I'm in the number 7, the property. What does number 7 property say? Like, limit z equals c. Oh, okay.
Just the limit of a number is just a number.
Oh,
Doesn't matter what what x is approaching. There's no x in it,
okay.
right? The limit of a constant is just a constant.
Okay.
That's all we're saying. Is that okay? Okay. Sure. Number 10 says the limit as x approaches a of the square root of the nth root of x is just equal to the nth root of a. How would we prove that?
You can make it 1 over n.
Yeah. Yeah, you just make the exponent, the nth root is 1 over n as an exponent, and then it's the same process as before. Very good. So we could update this to really be positive rational number now, right? Combining those two together, I guess I don't need to erase that. It's fine. And if I look at number 11, this is basically taking that property 6 way at the beginning and doing the same, making the same argument we just made for the previous one, right? It's the same idea. Quick question before we move. Oops. Why do I need this piece? Why is that also included? It's like an extra criteria that seems like...
Normally, like, could be plus or minus. Wait, no.
Not quite, but...
What number is 10?
Well, it's got the same condition there, basically, right? That the thing underneath the radical has to be positive if the index is even. Yeah, so even radicals you can't do if you have a negative value, like the square root of a negative or 4th root of a negative or 6th root of a negative, you can't do. So here it's just assuming that, like, hey, if you have an even index, assume it's a problem you can do, and then you can do this, right? Because why would we want to take the limit of something that doesn't exist anyways, right? Like, everybody's okay with that? All right. So let's practice using these properties. So let's do part A here together, and then I think after that, I think that's probably going to be sufficient. So we start by, say, using property number 1. That allows me to break the limit at the plus sign. And then maybe let's use property 2. That allows me to break the limit at the subtraction sign. Oops. Come on, erase for me. Erase. There we go. Everybody feel okay so far?
Why did you separate 4 from the rest? Like, make it isolated and then left 2x squared minus 3x?
Because if I look at property 1, only allows me to separate a plus, right?
Oh, I
So I just separated the part that was added. And property 2 allows me to subtract or do the subtraction, so I only separate the stuff that was being subtracted. I'm just going step by step using one property at a time, right? Does that feel okay?
Yes, thank you.
Sure. Now I'm going to use property 3 to pull the constants out front. Oops. And then I'm going to use property, oh shoot, I think it's, I guess I could call it 6 or I could call it 9. It doesn't really matter. Let's use 9, I guess. That's more specific. And then I can use property 8 oops, forgot my limit here. Let me write that in real quick. And then I can use property 7, and that gets rid of my last limit. Christian? So we're going to see real quick why I'm going to skip doing the other example. Okay, so just hold that for just 1 second. So take a look at what we started with and what we ended with. What did I do? I just plugged A in for X, right?
Yeah.
That's all that happened, right? So look at the next property. This is called the direct substitution property. It says if f is a polynomial or rational function and a is in the domain of f, then the limit as x approaches a of f of x is just equal to f of a. So to answer your question, Christian, most of the time you're just going to be doing direct substitution. You don't need to name any property at all. Chanel.
Where did you get the a square and stuff? Where's this number 9? How'd you get a square from the limit x?
So number 9 says this, right?
So,
I had the limit as x approaches a of x squared, where n is 2, so it should just be a squared, right?
oh, because it's 2 limit
So
of x.
this
Yeah.
turned into that,
Oh, I understand. I got it.
right? Okay. Okay. So what's the catch though, folks? As long as A is in the domain of F. Go back to Algebra 2. That's a long time ago. What's the domain of any polynomial? All real numbers. So is this going to work every time if f of x is a polynomial? Yes. You don't have to think about it. What's the domain for a rational function?
All rational.
Nope. It's all real numbers except, close, where the denominator is equal to 0, right? So that's the place where we're going to have to be careful, because if I substitute that in and I get a 0 denominator, couldn't have used direct substitution. It's not okay to use it in that sense, in that case. And then we have to remember this is only good for polynomial and rational functions so far. I say so far. So for example, let's look at number 3, or this example 3. Can I use direct substitution on example 3?
No.
No, it's a rational function, but what happens if I plug it in?
The one,
If I plug the 1 in,
it's 0.
I get a 0 denominator, right? In fact, I don't just get a 0 denominator, I get 0 over 0. This is called indeterminate. It's not even undefined. There are actually 6 indeterminate forms. We'll talk a lot more about this in a future chapter. Those 6 indeterminate forms are 0 over 0, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. Indeterminate does not mean undefined. In fact, it means like you can't determine a value for this, because I can give you an example of a limit that goes to 0 over 0 that actually evaluates to 1 or 2 or 3 or 4 or 5. I can give you a different example that actually is 0 over 0, but actually evaluates out to different numbers. So we can't do direct substitution on this because we have a 0 over 0 situation. What should I do instead?
The properties, I don't know.
What could I do instead?
The division property, do the first
Nope, because again, it'll give me a 0 denominator. What can I do instead? Great, how would I do that? Factoring, yeah. How does that numerator factor?
x plus 1, x minus 1.
Excellent. What do you notice happens then? Everybody's okay to hear? Is what I've written completely correct? Right? We have to be a little bit careful here. Remember back in Algebra 2, when we do this, we can say stuff like this, but we also have to include like a restricted value, which is exactly where we're trying to evaluate with the direct substitution. Right? So we'd actually like, so the question is, can I do direct substitution if that thing is not in the, if what I'm trying to substitute is not in the domain? No, right? The rule before says that I can't. But let's look at this new theorem that we're giving here. It says if f of x is equal to g of x for every place except at a, then the limit of f of x is equal to the limit of g of x, provided that limit exists. Think about that for a second. What do we have here? This is like my f of x, and this is like my g of x, and that's like my a, right? F of x is equal to g of x everywhere except at one specific value. So what does that tell me? That I can do that, and my limit is 2. So all this is saying, all this property is saying, is that you can just reduce rational functions. You don't have to worry about the restricted values if we're talking about limits. As long as you're talking about a limit, reduce all the stuff you want. Don't have to worry about the restrictions. Even if the restriction occurs at what you're trying to do a direct substitution with, it's fine. You want to know why? So if I look at the graph of this. Oops. It looks like this, right? The limit as x approaches 1 is 2. If I look at the graph of this, its limit as x approaches 1 is still 2. Even though that piece is like undefined there, it's fine. The limits are still the same at that point. It's okay. That's basically what we're doing, right? We're just replacing a thing with a removable discontinuity with a function that's continuous. We've plugged that removable discontinuity with the point that should go there. If all we're doing is limits, both limits should be the same, whether that point's open or closed. It's fine. Does that make sense as to why we're able to do this? Now, this is like extremely subtle and like theoretical, what we're talking about right now, right? I'm trying to like do it as concretely and numerically as possible to like give you the right intuition. But basically what all this is saying is that you can reduce all the stuff you want. You don't have to worry about restricted values and just continue direct substituting as you'd want to, right? Most of us wouldn't have thought when I reduced that to worry about the restricted value anyways. So it's just one of those. It's okay. It's okay is what we're basically saying. Let's do some more examples. Because this is now getting into just evaluating limits without a calculator, right? Which is what we want to get to. All right. Next one says limit as x approaches 1 of g of x. And g of x is given as the piecewise function. What? I mean, you could graph this if you wanted to. You do not need to do it to do it. What do we think? I'm going to write down what it's equal to. Why? Why is that okay for me to write? If I look, g of x is x plus 2 everywhere except for one place. So it is this definition exactly. And now, since I've rewritten it as x plus 1, I can just do my direct substitution and I'm done. If you wanted to think about this graphically, you could do that. Not hard to graph this without a graphing calculator, right? So we have our line everywhere but at 1. It just looks like the line y equals x plus 1. And then at 1, we have the point 1 comma pi. What's the limit as x approaches 1 of this? Two. Does it matter that at 1 it evaluates to pi? No. Does that feel okay? Now, I would do it this way if I were doing it, but you could certainly do this. Would not be wrong to just sketch a quick graph and use the graph to do it, even if it's like a no calculator question. Everybody's okay? All right. If something's not clear, you need me to say it again, or you just need a minute to think, stop me and say something. Happy to do it. Okay? It's important that we're getting what we need to out of our time here. So if you have questions, stop and ask me to slow down or repeat or whatever. Okay? We should stop and take a quick break here, right? We've been at this for a minute. I told you guys last time that we should, you guys should stop me halfway through for a break. Everybody stand up. Arms up. Stretch them out. Arms up high. Reach for the ceiling. Out to your sides. Get wide. Grab that floor. Little twist. Secondary goal, by the end of the semester, let's try to touch the floor, right? Oh, sure, no problem. Thanks, Anthony. Uh-oh. That's our minute. Who feels a little bit better? A little more awake? It helps a little bit. All right. Example 5. Okay. Can we do a direct substitution on this? I mean, if you do, you get 0 over 0, right? So it can't say anything about it. You doing that, but there is still things we can do, right? Just because a direct substitution gives us 0 over 0 doesn't mean there's nothing to do. What could we do with this? Yeah. So if we FOIL this out, what do we get?
Plus 6
Great. Good job with your mental maths. Okay. What do you notice now?
You can like cross out that.
Great. Keep going. What else do we notice?
Can you factor more?
You can factor out an h. Yeah. And now, even though we're reducing, we can just reduce willy-nilly. We know that it doesn't affect our limits. And if I do my direct substitution, I get 6. Yay! I went from something that algebraically looked rough into something that was like, oh, that's not so bad. And remember, if you have no graphing calculator to use, trying to generate a graph of that thing or a table for that thing, barfaroni, right? That's going to take a long, long time, as opposed to this, which was a minute, if you saw what to do right away. Is everybody okay? Okay. Let's look at another one. So here we have the limit as t approaches 0 of the square root of t squared plus 9 minus 3 over t squared. If I try direct substitution, what do I get? 0 over 0. Wah, wah, wah. Okay. Well, is there something we can do still? And t squared plus 9 does not factor because it's a sum of two squares. Okay, by what? Yeah, so we'll multiply by the conjugate. That's what that's called. So I'll elaborate here in a minute after I write down what Giselle just said, because some of us are looking at this and go, where in the heck did she pull that from? So this is the idea. So remember, if I multiply two conjugates together, the result is a difference of two squares, right? This is a great option Because what happens if, like, in our case, a is like the square root of t squared plus 9, and b is 3. When I look at a squared, what's going to happen? The squared's going to cancel the square root. Oh! And then what's b squared? 9. So I'm just going to end up with like t squared plus 9 minus 9, and great things start happening. So those cancel out. Now what can we do? The plus 9 and minus 9 cancel. And the t squareds can cancel. So that's what's left. Can I direct substitute that? You betcha. Woo! That multiplying by a conjugate is a good one to remember. Oftentimes when you see a radical plus something or minus something, use that conjugate. Good things happen. How are we doing so far? So far, so good? Okay. So, again, this rehashes the definition of a limit existing back from last chapter or last section. So the limit as x approaches a of L, or limit of x approaches a of f of x is equal to L if and only if the left-hand limit and the right-hand limit both equal L. So that being said, we need to show that the limit as x approaches 0 of the absolute value of x is equal to 0. And in fact, maybe I should say prove, because I don't want us to use a calculator to graph this. And I don't want us to do a table. I want us to do this algebraically. Can I do direct substitution on this? No. The reason I cannot is the function is not a polynomial or a rational function. This is an absolute value function. So direct substitution is not applicable here the way it's currently written. However, if I think way back in time, the definition of an absolute value is the piecewise function as such. The absolute value of x is equal to x when x is non-negative, and it's equal to negative x if x is negative. Chanel?
Wait, so just to make sure, so direct substitution can only be used on a polynomial rational function, no other types of functions?
As of this moment, that is what we're saying.
Oh, okay.
We may expand that definition, but as of right now, that is what we are saying.
Okay.
Everybody okay, remember this definition? Maybe, or if you didn't, be like, I don't know if I've ever seen that, but if you look at it, be like, okay, that sure works. What's the advantage of this? Yeah. Is I can say this since I need to show the left-hand limits and the right-hand limit are both 0, by doing the left-hand limit, I'm isolating here, so I can make that replacement, and now I have a polynomial, so I can direct substitute. Similarly, by looking at the right-hand limit, I'm limiting myself to this part of my piecewise function, which allows me to replace it with this, and again, now direct substitution is applicable because I have a polynomial. Okay. The next one says, prove that the limit as x approaches 0 of the absolute value of x over x does not exist. So what are we going to know here? Is that the left-hand limit and the right-hand limit have to be different, right? If the limit doesn't exist. So I know immediately I'm going to be interested in this. And I'm going to be interested in this limit. Everybody's okay? I'm going to again use the definition from above. So since I'm approaching 0 from the left, I know my x's are negative. And here, since I'm approaching 0 from the right, I know my x's are positive, so I can make the appropriate substitutions with my piecewise definition of the absolute value function. Leaving me a constant. I know a constant is something I can take the limit of. And since they're different, I know that the big limit doesn't exist.
Where did you get the negative 1 and 1 from? Is it just like any value you pick that's like...
I mean, I reduced, right?
Oh, okay.
So just... But yeah, I mean, it's the same idea.
Okay.
Yeah. Okay. Do this one more and then we'll probably be stopping because I want to be able to do a good job on talking about the squeeze theorem. That's an important one, and I don't want to start that with like 4 minutes left or something and just try to like cram it down our throats all at once really quick. We'll take our time. All right. Determine whether the limit as x approaches 4 of f of x exists. So to do that, again, we need to look at the left-hand limit, and we need to look at the right-hand limit. Everybody okay? So far, so good? So if I'm looking at the left-hand limit, I'm looking at this, right? That's what f of x is. I'm looking at an x less than 4. So I'll make that substitution. Can I do direct substitution on this now?
Yeah.
Yes. Because it's a polynomial. Everybody feel good? Now let's do the next one. So again, because we're looking at from the right, we're looking at the x is bigger than 4. Can I do direct substitution on this? No, because my function is not polynomial or rational. It's a radical function. However, if I go back and look at property 11, let me scroll back so we can see it. Look at what I can do. I can take my limit sign and just stick it underneath the radical. That's the tool that I'm going to use to get myself into a place where I can do direct substitution. Everybody's good with that? Now this piece, I can direct substitute. So what would I conclude here? And it's, in fact, it's equal to 0. Chanel?
Wait, so how come like before you could like substitute it, but then now that you put that radical over it, over the limit, you could now substitute it?
Because all I did was take the limit of x minus 4.
Okay.
Right? X minus 4 is a polynomial.
Oh.
That I can do direct substitution on. And then I take my answer and square root it afterwards.
Oh, I understand.
So
Okay.
because I was able to push the limit underneath the radical, I get it to be a polynomial now that I'm doing direct substitution on, and it's okay.
Okay.
As opposed to before where I was trying to direct substitute into a radical function,
Okay.
which I couldn't do.
So it would just be 0, the answer?
So my answer, while it asks determine if that limit exists, the answer is yes, and it's equal to 0.
Got it. Thank you.
Nolan.
So for the barbers, like then when it goes from the on the square root, then x approaches 4, x minus 4, and it becomes that part becomes 4, but it's
So I did a direct substitution here.
yeah. Oh yeah. Okay.
So I just dropped the 4 in for x and then took the square root of the answer. So here I'm gonna make a little edit. Well, that's not even right, is it? Yeah, so we're doing 2.3. We didn't finish 2.3. And these aren't even the correct boldface things. Okay, go away. So I want to, 37 is a squeeze theorem thing. We haven't talked about that yet. That makes no sense for me to expect that to be on the homework quiz. So I'm just going to replace problem 37 with problem 26 is one you were going to be doing anyways. I'll just bold that one. How about I do this? That good? That's probably better.
Yeah.
Sure. Dang it.
Are we still doing it for 37 now?
We are. It's just wouldn't be a homework quiz question because, well, we didn't talk about the squeeze theorem. How are you supposed to be able to do something, use a theorem we haven't talked about, right? So again, this homework, once you get to the end, if you're like, yo, I don't know what things they're talking about, just skip it. We still have a little bit left to do in 2-3. So you should be able to get should be fine up until 36, 37. And then even some of those after that I think would be okay, but maybe not all of them. But the bold stuff you can do. All the bold stuff is doable.
This homework's due on Sunday, right?
Well, this homework set would not be part of Sundays because we wouldn't have it. Oh, yeah, it would be because we have Thursday. Yeah, I'm done. Yes, this will be part of Sunday's homework set. Yeah, that's right. Everybody's okay?
Yeah, so we have homework quiz in this next class.
Yes. And this will really be like the start of every class. It'll be like homework quiz more often than not. But you get partners. You get to use all your notes and all your homework that you've written for it, right? Like it's not that bad. It's a little stressful because you got to make sure you've done at least 5 or 6 of these before next class. But I think it's really going to help pay dividends of making you think deeply about some of the homework at least before we get to class, you know?